All right, ladies and gentlemen. So this just to continue working out this question here. So I would have just posted a lesson previously. Um, really talking about Kirchhoff and the EMF and all that kind of crazy stuff, right? So just recap that the EMF of a cell is the total amount of energy provided by the cell to each coulombs of charge passing through the um, the circuit basically. The terminal voltage is the work done by the cell to flow or in flowing rather a unit of charge from one terminal to the other through the external resistors or resistance in a circuit. So maybe you can take note of that as well of a definition for EMF and terminal potential or terminal voltage. Now here we have a Kirchhoff question in, and it wants us to calculate the current flowing through the 12 volt battery. Now as you can observe from this circuit, right, A and B right here is not connected to the circuit. You have an open circuit right here. So this part of the circuit is not included. So what it means now that what we're looking at is all of these things here around here that would make up this entire circuit right now. So this 5 volt battery and this 1 ohms internal resistor, right, will not be incorporated in this. So what we're looking at basically now is a complete series circuit around here, right? So we're looking at a series circuit. So what is connected in series? So we have the 12 volt connected in series. We have this 1 ohm. We have this 1 ohm. We have this battery with its internal resistance. We have this 2 ohms resistor. We have this 2 ohms resistor. We have this internal resistance again. So that is what is happening here, ladies and gentlemen. So best thing to do whenever we have a simple series circuit, we want to find the current flowing through the 12 volts. So for us to do this, we can use Kirchhoff's law, because this right now is one loop completely, right? It's one complete loop. And what you must understand is that in series, the current flowing through this battery is going to be the same current flowing throughout all of these components. So it makes life a little bit more easier for us. So we could start off with Kirchhoff voltage law that says sum of the EMF is equal to sum of the potential drop across each of these resistors, right? Now, as I said before, that the current is going to be constant because of the series circuit. So having said that, sum of the EMF here, because the 12 volt, the negative terminal, right, is essentially connected to the negative terminal here, then that means that we have to subtract these two. So 12 minus 8, right, would be my total EMF, or the sum of my EMF, is equal to the sum of the potential drop across each component. We're trying to find I is constant. Now R right here is going to be my total resistance in this series circuit, and that is essentially going to be, if I add up all of these resistance, so we have to incorporate the internal resistance here. So this is one resistor. So we have 1 plus this 1 plus this 1 right here. That's adding up our total resistance. And by the way, you should know by now that whenever you're finding the total resistance in a series circuit, we just simply add them up, right? Right, 2 plus 2, I believe that is. So that is what? 4 plus, how much of this we have? Let me check it again. So 1, 2, 3, 4. Okay. I need another one right here, right? So plus 1. So we have 8 as the total internal, well, as a total resistance times T and a T, but I rather. We subtract this, the 12 from 8, or 8 from 12 gives us 4 volts. Just simply transpose, divide both sides by 8. It means that I will become 0.5 amps. Now that we have that, right, we are complete with this question. Cool? So now the next part of the question is going to require for us to find out the current again that is flowing through the 12-volt battery, right? But in this case, it says that A and B are now connected by a piece of wire. So this is where now it kind of gets a little bit more complicated. Not say complicated, but it involves more of Kirchhoff. So this is now connected here, ladies and gentlemen. So one of the first things we must do is to identify our loop. So this is loop 1, or we can call it A, and then, all right, so we're flowing the current this way. If I'm flowing the current that way, I1, I2, I3. What I just did a while ago is to show where my currents are flowing essentially, right? I'm going to do something here just for your own benefit. I'm going to allow the current in this loop to flow that way as well. So this is loop B. When it comes down to Kirchhoff's current law, right? That's like kind of the easiest part. So I1 is the current flowing into the junction, so that's going to be equal to I2 plus I3. Now for loop A, we just want to establish what is happening here. As you can see in loop A, there are 2 EMFs, and the negative terminal is connected to the negative terminal of the other EMF. So KVL for loop A, we're simply saying the sum of the EMF is equal to the sum of the potential drop across each component. So in this case, I'm subtracting 12 from 7, right? Then I simply go ahead now and say, let's look at the EMF here. So, or the potential drop rather, potential drop across each component. So I have I1 times 1, right? Plus, so I2 is flowing through the internal resistance right here. So I2 times 1 again, I2 times 1, plus, so when the current reaches here, it's going to flow up. This current here is going to be I1, right? So that's something to note, that the entire current in this section is going to be classified as I1. So there's not going to be a different current, but it's going to be I1 that is flowing through that 2 ohms resistor. So I'm going to say I2 times 2. And what I just need to do now is to simplify this, right? Simplify it. Okay, but there's another resistance. Sorry about that. There's another resistance. I'm not finished. So this one right here is also incorporated here. So let me correct something. I said I1, but I put I2. So that's I1, right? And there is this other resistance, which is the internal resistance. So that's going to be plus I1 times 1. So by just simplifying this, we can get 5 is equal to, so we have 1 I1 plus 2I1, that's going to give us 3I1 plus another I1 that gives us 4I1. So 4I1, right, plus, I2 is equal to 5. So that's the first equation that we're going to hold on to. Then now we move from there, so right, and we're going to talk about loop B. All right. So when it comes on to loop B now, all right. So loop B, we're seeing where we're making the current flow this way. So in a sense, we now look at our EMF. Let's go ahead and see if we can subtract our EMF here. So the sum of the EMF is equal to the sum of the potential drop across each component. So we have, in this case, 8 minus 7 is equal to. So let's see here. All right. Now, I would have done something different in my notes here. I think it's the same. It's the same thing, man. I think it's the same thing. Yeah, it's the same thing. So let's not worry about that. So, all right. So let's now look at the potential drop. We can start out with this one right here. All right. So we're starting out with the current coming. So I3 flowing through this 1 ohm resistor. So I have I3 times 1, which is the same thing as I3 plus. Then now I3 is the same thing that's going to flow through this internal resistance. So I have another I3 here, right? Then I'm going to add that now to this voltage here, which is I3 again, but in this case multiplied by 2. And I'm not finished. I'm going to plus another one, which is this this internal resistance. Now this can be tricky because what you're essentially seeing here is that I2 is flowing in the opposite direction from where the current in the loop is flowing. So what that means is that rather than adding, I'm going to subtract. So to just compensate for the difference or for the change in the direction of the current, right? I just use a minus sign. So minus I2 times 1. So let me go back over that again. So every time when you're dealing with a Kirchhoff question, you have to choose where you want the current to flow to. See? So in loop B, my current is flowing clockwise. Now with that now, when I reach to this internal resistance here, I see that I2 is flowing in the opposite direction from where the current in the loop is flowing. So to just correct that, you just put a minus sign, all right? So by way of just simplifying that, we're going to get 1 is equal to 5I3 minus I2. Now, what I can do next, so I have now 2 equations. So I have equation 1 right here, and I have equation 2. Now, remember that we're trying to find the current flowing through the 12-volt battery, which is essentially I1. So we want to find I1, right? So here's where the mathematics comes into play now, right? So I'm going to look at both equations, and I'm going to see how best I can eliminate something, right? So that I can find one unknown, basically, right? And from that, we can then, we can then solve for the answer. So, but what the first thing I'm going to do here, right, is to go ahead, you see, and there's not one way of doing these things, guys, as you can imagine. So the first thing I will do here is to substitute, right, I1 into equation 1. So I'm going to sub for that. So when I do that, so right here I know that I1 is equal to I2 plus I3. So when I do that, I'm going to have 5 is equal to 4 I2. So in bracket I2 plus I3, close the bracket, plus I2. Right, then I just simplify it. So I have 5 is equal to So this is what 4i2 plus 1, so that's going to become 5i2 plus 4i3. So my new equation now, equation 3 for the most part, is that. And having this now, I can see that the equations are similar in terms of the fact that they have the same variables, I2 and I3. At first, the equation 1 and equation 2 did not have the same variables, so that pose some issue because I need the equations to look alike so that I can eliminate something. So now that I have these two equations, right, equation 3 and equation 2, then I can now utilize what we call the method of elimination, right? So what we're going to do now is to say one, you know, one is equal to 5i3 minus i2. Cool. And then now I have 5 is equal to 5. Let me just rewrite it so it looks a little bit better. So minus I2 plus 5i3. I'll just rearrange it. You understand? So that it looks a little bit more uniform. So right here we have these two equations, and I need to eliminate something. So when I look at these equations, ladies and gentlemen, what is it that I could possibly do to this equation here so that I can eliminate something? Right? You can pause and think about that. Because we're looking at math now. We want to get rid of one variable so that we can find one of the variables here. So the best thing for me to do, right, is to multiply this everything here by 5. Once I do that, I have 5 equal minus 5i2, right, plus 25i3, and we're going to now write back the data part. Now when you come on to the method of elimination, you can do two things. You could add or subtract. In this case, I have to add because this addition sign is going to affect everything. So 5 plus 5, right, is equal to minus 5 plus 5i2, right? So clearly this is going to cancel out. Then I have 25i3 plus 4i3. So I have 10 on this side is equal to 29i3. And all I need to do now is to just solve for i3. So by way of transposition, right, I can see that i3 is equal to 0.34 amps. So I'm making progress. The question volume 9 marks basically, guys. So you can imagine that it takes a lot of working out. So I'm going to erase a few stuff here. Practically, I'm going to erase everything because I need the space. So, I mean, you can definitely go back and pause the video to just see what was there. Right? So we just found out that I3. So we found out that I3 is equal to 0.34. Right? So having said all of that, we can now look back at one of the equations to find another unknown. So you look back at your equation. So because I know I3, I can find I2 using equation 2. The equation 2 tells us that 1 is equal to 5i3 minus i2. If I substitute I3 in this equation, then I have 1 times 5 times or well 1 is equal to 5 times 0 point 3 4 minus I2. When I do simplify that, right, and transpose to make I2 becomes the subject, the I2 is going to equal to um, 1 point, 1.5, 1.7 rather, minus 1. So I2 is now equal to 0.7 amps. So by way of using Kirchhoff's first law, I1 is equal to I2 plus I3. There might be an easier way to do it, but you know, maybe I haven't looked at it from that standpoint. So I1 here is equal to 1.4 amp. All right. So that's what you would have to do there. I hope this didn't take me too long because I mean we're trying to work with time as well. All right. So we kind of move on from that in a sense, right? Let me see here if I was prepared for this part. All right. So I might have to, record that part separately as it pertains to, how we call it now, operational amplifiers, right? But I mean, you can go ahead and try this to say that show that the closed loop gain, um, you know, of of a this particular non-inverting operational amplifier is given as such, right? And it says clearly state any assumption made, above about rather the properties of the operational amplifier. You know what I mean? Um, Operational amplifiers are very, fun stuff to talk about for the most part. Because what you have to understand, ladies and gentlemen, is that if I have a voltage at this terminal, right, it tells me that the voltage at the non-inverting terminal is the voltage that is at the inverting terminal, right? And so with that information, it now gives us a sense of what um, we call it now potential divider for the most part. We soon talk about potential divider, but let's see here. So if I consider um, the potential divider formula, right? So generally speaking, we whenever you use the potential divider formula, it is for us to find the voltage across a particular component, right? And the voltage across R1 is going to be the voltage that is at the at this terminal here, which is going to be uh, VI, right? So in most cases, you'll see the potential divider formula that says VI, right, is equal to um, the R Ri, right, which is the resistance across, well, yeah, the resistance across the, well, not across, but that's basically the resistance that we are talking about the voltage across in a sense. And potential divider formula is simple in a sense where you say, the resistance times the overall voltage, right? Um, Divided by the sum of the resistance. So in this case, we have two resistance here. So we have RI and RF, right? RF. RF, guys, is your feedback resistor. Um, and this V right here is essentially going to be your V out, which, yeah, that's going to be your V out. No, all we're simply doing, so the assumption that we have made here is that V in, right, is the voltage that is reflected or the voltage at the non-inverting is the same voltage that is at the inverting terminal. That's the assumption. So from there now, what we need to do is to transpose this equation so that we get V out upon in, because you must understand that gain, right, really speaks to how much the output has been amplified. So, or how much, let me say that, how much your input rather has been amplified. So it's V out upon V in tells you the gain. So we're looking to transpose the equation so much so that we have V out upon V in. So if I do that, I will have to bring this part across the equal sign as well. So we're doing two things at the same time. Right? So now that I have V out upon V in, I still need to transpose this and bring it across here. Once I do that, I have this now. So technically, this would cancel out on that side. So we have Ri plus Rf divided by R in is equal to V out upon V in, which is still equal to your gain, right? So it's nothing really hard. And I mean, it's clearly an easy 5 marks to get here. I don't think probably what I have done here really values 5 marks, but that's simply what is being required for us to do here. So what we're looking at is a potential divider that is being set up here, right? And if you know anything about the potential divider, this would be the equation that you would use whenever you're trying to find the voltage across a particular resistor, which is Ri. You follow me? So how you know it's a non-inverting operational amplifier? That is when the V in is connected to the non-inverting terminal. The non-inverting terminal is the positive terminal. The negative terminal is called the inverting terminal. So, ladies and gentlemen, what we expect here is that if the voltage that is at the non-inverting is a positive voltage, or we mean positive voltage, we mean that, you know, it starts out positive. So let's imagine that this is our graph. It starts out positive, goes negative, and alternating current. What it means that if this is V in, and we want to consider what does that mean at V out, right? Then it is still going to have that positiveness about it, in a sense. It's still going to be a positive wave, but the only difference is that it is being amplified, because operational amplifiers are used to amplify voltage. So we expect that it's going to be amplified, and it's not going to be inverted. But however, if we're talking about the inverting operational amplifier, what that means is that if my signal was positive at first, then it is now going to be in the opposite region, going to be in the opposite portion. So I would expect that the amplification output signal would look the opposite, right? So that's what we mean to say you're taking the input and you're inverting it, right? As it suggests inverting terminal, and you have one we call a non-inverting. All right. Now let's just see if we can work this question quickly. I mean, it wasn't in my scope of wanting to do this, but let's see here. So let's imagine that we have a circuit like the one in figure 4 is set up with a feedback resistor with that value and an input resistor of that value. It says that the operational amplifier, you know, basically have a supply of 5 volts, positive plus or minus 5 volts, right? Now that's the amount of voltage that the operational amplifier can basically give you, or it can amplify the voltage to that amount. Now the question is, what is the value of the output, you know, voltage, right, when the input voltage is this amount? So what we just simply need to understand is that V out upon V in is equal to R1 plus Rf divided by R in. So what we just need to do now is to transpose the equation to make V out become the subject. So V out is equal to R1 plus RF divided by this, and in bracket we just times V in. Nothing hard. So V out here is equal to 40K. You have to incorporate the K, guys. Alright, so just please remember that. So ohms is the unit by itself for resistance. If there's a K beside of it, you have to incorporate that, right, which is basically a prefix. Plus 440K divided by 40K times 250 millivolts. You have to put the milli, so that's times 10 to the minus 3. Now, if you fail to incorporate those things, then it's going to separate the ones from the twos, and slowly it's going to separate the twos from the threes as when the results come out, because we want you to pay attention to details. You follow me? That is the aim here. Most times the questions are not hard. It's just for you to just pay attention. You get what I mean? So having said that, we can simply solve this question in no time. So let me just quickly do that. So we have 40K, right? Plus 440K. When I add up all of that, I get 480,000 divided by 40K. I got 12 when I did that part. I'm going to multiply that by 250 times 10 to the minus 3. So 12 times 250 times 10 to the minus 3. So what I got a while ago was that V out is equal to 3 volts. See? So once you get this now, it tells you that the voltage is 3 volts. Now, what you must understand is that if the voltage is 3 volts, then it means that the operational amplifier has not saturated, right? It has not saturated. So that's good for the most part. And but what we mean by saturation is when the operational amplifier gives it maximum output. And what that looks like is a graph looking of this nature. So to be saturated, you would see a graph looking like this. Now, the reason for this, flat region is because, generally speaking, the wave is alternating, right? And if the output is more than what the operational amplifier can supply, then it is going to perform a process of what we call clipping. It's going to clip off the excess and basically clamp you to the amount that it can provide, which is 5 plus or minus 5, right? So that is what you're seeing here. So these parts are being clipped off. If the voltage exceeds the amount that the operational amplifier can provide, and for that we say that it has become saturated, right? But however, in this case, we see that the thing is 3, so it therefore means that it has not saturated. So you will still see your graph looking as beautiful as you can imagine. Well, I cannot draw this incorrectly, but it's not going to clip off. It's going to look as such. So the question continues, right? And it asks us, it says, if the operational amplifier is not saturated, it says what is the maximum, input, amplitude rather, for the input signal. This question is so tricky because what you must also understand, guys, is that just as the amplifier reaches its maximum output, right, which is 5, that is the point when the operational amplifier will not saturate, and also it is the point to which saturation will also take place. So it's a very tricky thing. So you're on the borderline, you understand, of saturation and not saturation. So that's the best way to look at it. So once you have your amplifier, before it can saturate is just when it reaches uh, 5, which is the maximum input, maximum output rather, or maximum voltage supplied to it. So here they just want us to know find the maximum input, you know, that the non-inverting terminal can have to prevent saturation. So just before saturation is when your output has to be 5. So in this case, we are finding the V in. So let's just write back our equation that says V out upon V in is equal to, you know, Ri plus Rf, right, times Ri, right? So we want to find V out. So we just need to transpose. We just bring things across. No, we want to find V in rather, right? So we need to just say R1 times V out divided by R1 plus Rf is equal to V in. So by way of just putting in those values, so we have 40K times V out, which is 5, divided by 40K plus 440K. That will tell me V in. So once I do that, so let's work that out. So we have 40K times 5. Our numerator is going to be 200,000, and that is now divided by I believe 480, right? So 200 divided by 480,000. Then that just tells me that V in has to be 0.41 or 0.42 volts, right? That's what V in has to be. So I think I will leave it there at the moment. But the question I think continues. You know, right? I think it continues. But I think that's a different part of the question. Maybe a different part or a different question in itself. But you can look at it for your own benefit and see if you can answer that part, right? So that's it for this portion until we continue and talk about other things, right? As you can see, there's a lot more stuff that we need to discuss, of course, and practice. But that's it for now.